Bismillahirrahmanirrahim. I hope you have got a really good midterm exam. So after midterm, we will be looking at the first law of thermodynamics and the second law of thermodynamics. So today lecture, it is the first law of thermodynamics and first law of thermodynamics for the controlled mass system. Uh, we'll be defining it later a little bit. In the previous lectures, we introduced different properties, different state functions, different path functions. In the last lecture, we introduced two different kind of energies, heat energy and work energy. And we were saying like these two different kind of energy can change the state of the system. Today, we'll be quantifying these changes, that how much heat was supplied, how much work was done, or how much work was supplied, how much heat was produced, or how much heat was in actual supply, how much work was in actual done. So today we will be looking at the first law of thermodynamics. In a previous lecture, we did introduce one of the other law, and that was actually the zeroth law of thermodynamics. And in that lecture, I did select uh, the we would be having some observation, and that observation would lead us to define a law, and that law would be actually defined using a different property or a property. So in zeroth law of thermodynamics, we had got an observation, and that observation was thermal equilibrium. And that thermal equilibrium was defined using a law, using a properties, and that property was called as temperature. Today, again, we would be looking at the phenomena, and that phenomena is called as the conservation of mass and conservation of energy. And that phenomena would be defined using two different property, and if I would say like different properties called as energies. So you might know different kind of energies. A system energy can be sum of internal energy, kinetic energy, potential energy, chemical energy, electrical energy, magnetic energy, and you can imagine so different kind of energies. Um, so in other words, if I would say like these two different, you might be familiar with the kinetic energy, you might be familiar with the potential energy, you might be familiar with the chemical energy. Let's have another, today we have introduced another kind of energy, which is actually the internal energy. Internal energy, how internal energy is arising. Internal energy arises from the random and disorganized motion of the molecule. When there is disorganization and randomization of the molecules, then we would be saying like there is an internal energy in the system. In a previous classes, you might have actually said like internal energy is the sum of kinetic energy and potential energy. Sorry, in classical thermodynamics, that definition might not be good enough, or if I was like not that might not be actually correct one. So kinetic energy, internal energy, which is equal to sum of kinetic energy and potential energy, is actually in terms of microscopic thermodynamics, or microscopically, if we are defining the internal energy, then that is what we call it as the sum of kinetic and potential energy. But if we are defining the macroscopic, so macroscopic does not mean like internal energy is sum of kinetic and potential energy. In other words, if I would say like, let's say, if I would just make this system open, let's say, for example, this system is open, and actually mass is moving into the system and mass is leaving the system. So if mass is moving into and leaving the system, then we can define that the internal energy would be actually change in the energy of themselves to system. And if I would say like the molecules are itself changing the position, or molecule are changing from low potential to higher potential, then we can define that there would be some potential energy as well. But if I would just close this system, if I would say like close this system, then what you would be suggesting, would there be any internal energy? So if you are saying like internal energy sum of kinetic energy and potential energy, so that means like, and by that definition there would be no potential energy and kinetic energy, so there would be no internal energy as well. So that means like you are confusing yourself with two different things. the microscopic and the macroscopic. So microscopically, kinetic and potential energy of the molecules can be related to the internal energy. But in a macroscopic, kinetic energy is mostly related to the flow of the system or the flow of the molecules, and potential energy obviously the potential of the molecules, while it is does not relate to the internal function of the molecule itself. So internal energy, kinetic energy, and potential energy, we would be dealing with these different kind of energy differently. So as I say again, arise from the randomization and disorganization motion of the molecule. So we will be restricting ourselves to this simple definition in a macroscopic level. If you can imagine again, these randomization and disorganization motion would increase if we increase the temperature. It will decrease if we decrease the temperature. So that means like this motion of the molecule is a primary function of the temperature. So internal energy itself is a function of temperature, and sometimes it is called as the thermal energy. So if we are increasing the temperature, internal energy would be increasing. If we are decreasing the temperature, the internal energy would be decreasing. So that means like it's a function of temperature and it's called a thermal energy. As this again arise from the randomization and disorganization motion of the molecules. At the molecular level, we are defining it. So we are defining it as a state function. So internal energy is a state function. That means like we are changing from T1 to T2 actually. So we will be only interested in the what actually was internal energy U1 at the start and what would be internal energy U2 at the final, and we would be looking at the difference between them two. We will be now looking at how the internal energy, how the temperature is changed from one form to another form, but we are just looking for the temperature change and the internal energy change. Recall like for the pure substance, the entire state of the system was specified by the two independent intensive property. So that means like if you are defining the internal energy, we would be defining internal energy as a function of pressure and temperature, as a function of pressure and volume, as a function of volume and temperature. So if you want to find out the internal energy, you can find out with these two independent properties. Now let's go move forward to and let's move forward to the first law of thermodynamics. Before we actually come to this equation, let me introduce something. Let me have a different um, example, and that example would be, I would say, would be easy to understand this. Sorry for that. Let me rub it out, or if not, then have another page. Okay, let me rub it out then. Okay, so let's say the same example, and the same example of piston and cylinder. So we have got a piston in here. Sorry, we have got a cylinder, and we have got covered with a piston in here. So we have got a piston and cylinder, and let it be. We have got the system volume, and that volume is actually, or the system mass. That mass is actually fixed. So we are looking at the controlled mass system, and we have got inside that piston, we have got, let's suppose, some gas in a system. Let's say we say like we have got a fluid in it, and if I supply some heat to it, and that heat is supplied in form of Q, let's say. So if I supply heat to it, so there would be in a simple way, there would be actually change in the pressure. That change in the pressure would result into change in the volume, and the piston will rise. If the piston is not fixed, it will rise, and obviously there will be some work done, and that work done will be equal to W. So if there is no losses or there is no other changes inside the system, so that means like the total heat supplied to the system would be equal to the work done in a system. That will be equal to this one. But no, sometime in a mostly cases, this dq is not equal to dw. That what I mean to say, like whatever you are supplying heat to the system, it is definitely not reflected in terms of w. So there would be some change in the energy into the system. Another term, what actually I mean to say, like if you are supplying heat to the system, there would be some energy changes into the system, and there would be some work done. So this heat transfer is not only equal to the work done, but there would be some change in the energy as well. Now let's define different kind of energy in it. So there can be equal to the, as we have said, like it could be equal to internal energy, it could be equal to kinetic energy, it could be equal to the potential energy and chemical energy, and so on and so forth. We can have different kind of energy. So yes, if you are supplying heat to the system, it could change in the internal energy plus kinetic energy plus potential energy plus chemical energy. For a simple system, let's ignore the chemical energy. We are not dealing with the combustion or something like this, so we will be looking at the not looking at the chemical energy. But what about the kinetic and potential energy? As the mass is fixed, as there is no change of mass into and out of the system, there is no movement of the mass into and out of the system, so definitely there is no kinetic energy changes. As the system is again fixed, as there is no movement or there is no potential movement, so the potential energy is also not there, or there is no changes potential, no change in the potential energy. So the only energy now change in energy would be the internal energy changes. So our equation, which was somewhere here, is reduced now for the control mass system. It will be reduced that change in heat would be equal to change in internal energy plus the work done. Or in other words, the change in internal energy is equal to the heat supplied minus work done. This is the first law of thermodynamics. So what actually the first law of thermodynamics say, like the change in energy of the system is equal to the difference between the heat supplied and the work done. For a control mass system, as we have said, like there is, then in this situation we do not have got the potential energy, we do not have got the kinetic energy, we do not have got the chemical energy, so we are only restricting ourselves to internal energy. So for the control mass system, we will be only having the internal energy, and that internal energy is equal to the heat supply and work done. So the first law of thermodynamics is now equal to change in internal energy is equal to heat supply minus work done. Now note these two different properties in it, the heat supplied and the work done. So heat supplied is the path function, work done is the path function. But what about the internal energy? We define the internal energy just recently now, internal energy as the state function. So that means, like, although Q is a path function, W is a path function, but the internal energy is not a path function, it's a state function. Please note also the symbol d, du, and partial q and partial w and du. If you can notice, like the for the path function we have written the partial for the path function, for the state function we have written the u, the exact differential. So let me clear it out. Let's say we did define in a previous, let's say I've got pressure change, I've got expansion and expansion from, let's say, state 1 to state 2, and I'm changing from volume V1 to V2 and pressure V1 to V2. So, and I'm doing the isothermal process. So to define the, or to find the work done under the curve, if I say, like, I would actually divide this path in a very small steps. That mean, like, my differential will be not exact differential. That mean, like, I would be dividing the whole path in a very small steps. You can call it as a quasi equilibrium steps, and in that quasi equilibrium step only and only I would be actually finding the work done. So this kind of a work done would be inexact differential. While for the state property, if I would just say, like, for the state property, you do not need to define the path itself. The only you need to define what was the state at what was the condition at state 1 and what was the condition at state 2, and just you just find the difference between 1 and 2, and you just find the internal energy or the state property change. So that means like the state function is actually the exact differential, while the path function is actually the inexact differential. Sign are most important as well. We define the work done to be positive when work is done by the system, and negative and one work done on the system. We would define heat to be positive when it is transferred to the system, and it will be defined negative when the heat is leaving the system. So in our previous example, if I'm supplying heat to the system, it would be the positive, and if it is work done by the system, it will be the positive work done. But if it is the heat is leaving the system, it will be negative work, negative heat, and if it is work done on a system, it will be negative work. So that means like our convention would be something like this. And yes, we did state this in our example. But again, note that if this form of first law were given as the control mass, as the mass was fixed, and we are situation, and in this situation we are dealing with the fixed mass. For the control volume system, or when the mass is changing, we would be calling this the first law of thermodynamics for the control volume system, and that's our next lecture. Let's have a little bit discussion on the first law of thermodynamics, and let's say have a corollaries of the first law of thermodynamics. So let me write it again. So the change in internal energy is equal to the heat supplied minus work done. And let's say the first calorie is, what if the process is adiabatic process. So if the process is adiabatic process, that means like the heat supplied is equal to 0. So if the heat supplied is equal to 0, the change in internal energy is equal to minus work done. So that would be equal to this one. What does that mean? So that means like if the internal energy is increasing, the work done is on the system. Or if in other words, if the work done is by the system, there would be negative internal energy. Let me define this over here. So that means if I'm saying like there is no heat supplied to the system, and we did say like there is only internal energy in here. So that if the work done is positive, work done is by the system, the work done is positive. So that in that case, there would be negative. I'm sorry for that. So work done is positive. There would be internal energy changes, and that internal energy change would be negative. And if the work done is negative, that internal energy changes would be positive something. In a simple way, if you can imagine, like if we have got work done by the system, so where this work done is coming from? This work done is coming from the change in the internal energy. So it is the internal energy stored in the system which is actually responsible for the change in the work done. So that means like the work is done on the expense of change in internal energy. So if there is positive work done, so the internal energy would be losing and we would be having negative internal energy. If work is done on the system, if I'll say like from the top actually, so you are increasing the pressure, you are increasing the decreasing the volume, so obviously there would be change in the internal energy, and that change in internal energy would be uh, a positive internal energy. So that means like in a other word, so the work done is on the expense of change in internal energy. Please recall the internal energy is also a function of temperature, and please also check what happened inside the internal combustion engine when we have got the process adiabatic process, and the work is done by the expense of changes in internal energy. Now, in this equation, as the work done is a path function and internal energy is a state function, so now the work as I select internal energy is a state function, so work done can now be found as a function of the state. So function of the state, it is simple. Just need to have two different um, uh, properties at two different state, and you can find the change in the state actually. For a cyclic process, the work heat and work transfer are numerically equal. Let me have this one. For a cyclic process, in a cyclic process, what would happen if I've got internal energy U1 in a state 1, and if I've got internal energy U2 in a state 2 actually. So I'm going into state from state 1 to state 2, and then from 2 to 1. That means like for a cyclic process, the total change in the state is equal to 0. So that means like change in internal energy would be equal to 0. So for a cyclic process, it's 0. So that means like we would be having the change in the Q would be equal to change in W. So for a cyclic process, this is a cyclic integral. So for a cyclic process, heat supply would be equal to work done. So that means like there is unchanged, the energy, total energy is unchanged, the which is internal energy is unchanged.